Hello everyone. In this video, I will be going through topical exercise on carbohydrates. Let's begin with question 1. Question 1 is about asking you what makes a monosaccharide a monosaccharide. There are a few things you want to take note of what makes a monosaccharide. Typical characteristics. The first is that the ratio of carbon to hydrogen to oxygen is 1:2:1. But take note, this applies to monosaccharides. It does not apply to things like disaccharides, and it does not apply to polysaccharides. Okay, it only applies to monosaccharides, so please take note of that. Okay, with that knowledge in mind, let's dive in. First question, if you were to give a count of all the carbons and hydrogens and oxygens, you'll find that there are 4, 8, and 4. Right, that follows the ratio of 1:2:1, and that fits the idea of a monosaccharide. Another characteristic of monosaccharides or sugars is that they come with hydroxyl groups. Please take note that the spelling is hydroxyl, not hydroxide. They are two very different things. Some students say that a monosaccharide or carbohydrate needs to have a carboxyl group. This is not correct. A carboxyl group is an acid group. Okay, you find this in amino acids, you find this in fatty acids, but not in sugars. Okay, so there's no carboxyl group. Next, let's go to part 2. Here, I think the challenge is to make sense of what the color means. This represents oxygen, this represents hydrogen, white, black represents carbon. Some students also miss the hydrogen pointing behind. Okay, but if you can identify all the different atoms, you should get 3 carbons, 6 hydrogens, and 3 oxygens. And it also follows the ratio of 1:2:1, therefore making it a monosaccharide. Okay, next, question 3, or rather part 3. The challenge now comes when we don't show all the carbons. Okay, here you see one straight line, right? And they don't show all the carbons here. But make a point that at every intersection, there's one carbon. So here is one intersection. You expect to find a carbon over here. Here's another intersection. Here's another intersection. So actually in total, there's 1, 2, 3, 4, and 5 carbons. And if you give all the hydrogens a count and the oxygens a count, it actually follows the ratio of 1:2:1. Okay, the general simplified ratio. Therefore, it's a monosaccharide. Part 4 is the rather challenging one. If you look at this carbon skeleton over here, it's missing a lot of things. But remember, the idea of a carbon skeleton is that they omit very often showing you carbon or hydrogen, because these are the very standard things that make up a lot of this carbon skeleton. So we want to really save on writing. But one thing to take note is that at every turn or bend, you expect to find a carbon. And also, every carbon needs to make 4 bonds. So here's one bond and here's one bond to the adjacent carbon. That means it's still missing 2 more bonds. And often the additional remaining bonds are bonded to hydrogen. So that's the general rule of thumb I will adopt. As long as the carbon is bonded to has 4 bonds, then it's correct. So even this last carbon I've just drawn, this double bond here has 2 bonds, 1 bond above to hydrogen, another bond to the adjacent carbon. 4 bonds for every carbon. Okay, so if you give it a count, there are actually 5 carbons, 10 hydrogen, and 5 oxygens. And that applies the general ratio of 1:2:1. And you can also make reference to the hydroxyl groups present. That's part 4. Let's go to part 5. In part 5 is another carbon skeleton. So again, let's practice what we just done. At every bend, you'll find a carbon. Next, each carbon needs to have 4 bonds. Here I have 2 bonds ready. Therefore, 2 more bonds can be dedicated to bonding to hydrogen. Here should be another carbon. Then in total, you see 1 bond, 2 bonds, and 3 bonds. Therefore, there should be 1 more bond, and that should bond to hydrogen. This last carbon here, there's 1 bond, 2, 3, and therefore you should have 1 more hydrogen. So if we give it a count, there's 1, 2, 3, 4, 5, 6 hydrogens in total. 3 carbons and 3 oxygens, and it follows the general ratio of 1:2:1. Last but not least, question 6. Here, all of the atoms have been displayed. The only thing you have to take note is of the color. This represents oxygen, this represents hydrogen, black represents carbon. If you give it a quick count, it should be 3:8:3. This does not follow the general ratio of a monosaccharide. Therefore, it is not a monosaccharide. It does, however, have hydroxyl groups. So this is an O bonded to an H. So although it has hydroxyl groups, it does not have the general ratio. And therefore, actually, if you look across the board, one factor that also makes a sugar or monosaccharide is the presence of this particular group over here, a carbonyl group. Okay, carbonyl. You find that there's always a carbon double bonded to an oxygen. Okay, that seems to be one of the defining factors of a sugar. This one over here does not have a carbonyl group. Instead, actually, I think this molecule is glycerol. You find that there's one hydroxyl group here, another hydroxyl group over here, and another hydroxyl group over here. So actually, it can bond to 3 fatty acids. Okay, so that was question number 1. Oh, one last thing. Some students are asking, if you look at the diagram over here, you find that this particular triangle is this filled up triangle over here. If we scroll up, you also find there are some triangles that look like this, kind of like dashes. Okay, so sometimes we use triangles to represent where that functional group is pointing. What do I mean by that? When you see a sort of filled-in triangle, and then let's say they put maybe a H, hydrogen like that, it means to say that this particular hydrogen is pointing towards you, out of the paper. Let's say if the paper over the screen is a flat plane, this is pointing kind of towards you. If I draw something like that, it means that it's pointing away from the plane of the paper or the screen. Alright? And if I were to just do something like that, it means that this carbon, hydrogen, and hydrogen, they're on the same plane. Okay, so sometimes we use triangles to represent different planes of where it is pointing away or towards you. Okay, not that critical for biology, but I think chemistry you encounter it more. Now question 2, state the name of the bond holding the 2 glucose molecules together. It is a glycosidic bond. It is not a peptide bond. Okay, peptide bond, you find it in proteins. Okay, so just take note. Some students say alpha bond. There's no such thing as an alpha bond. Okay, so take note, it's a glycosidic bond. Next question, 2b. I'd like you to read the question carefully. They said, with the aid of a diagram. Very few students actually drew a diagram in. So you have to draw a diagram to complement your writing. This is a sample of a diagram you can draw. On the left, you can draw the disaccharide. And then on the right, you can draw the 2 monosaccharides. But what you can also draw is the addition of water in between, because that's what hydrolysis is, right? So you will be awarded a mark if you have water being included. Okay, and you also, if you draw the correct structure of the sugar at the end of the day, you also want to make mention to the word hydrolysis. Hydrolysis occurs by the addition of water molecule. So some students did not take note of the addition of water molecules. There are some students that didn't read the question carefully. They didn't see that it's the idea of breaking, and they mentioned condensation instead. So condensation, you expect that water is produced. Okay, but in hydrolysis, water is used. Okay, in this case, we are actually looking at hydrolysis. So this is part B. Next, we'll go to part C. Describe how the structure of starch contributes to its function as a storage molecule. So you want to make reference to the structure. Okay, One response you can give is that starch is helically coiled into a compact structure, allowing as many glucose molecules to be stored as possible within a small volume. Now, what does this mean? Okay, so I give you an example. Let's say I have only this much volume of space, right? And let's say I have maybe 100 glucose molecules. If I were to join the glucose molecules one after another into a long chain, actually you'll find that it's very hard for me to pack these long chains into this volume of space, right? The long chains may not even fit, right? They may end up sticking out of this box, this volume. Instead, however, let's say I have the same volume over here, and I still make use of 100 glucose molecules, but this time, the 100 glucose molecules are attached in a way that they form this helical shape. And in a sense, right, I can pack more per unit volume. See, now I can pack a lot more glucose in a smaller volume of space, because for that same number of glucose, it forms this helical formation and it takes up less space as compared to a straight line. Right? If you have a straight line, imagine you try to pack a lot of chopsticks into a small box, right? You have chopsticks sticking out here and there. It doesn't quite fit into that volume of space. But if you have a lot of springs, however, these springs are much more compact. If I were to instead, unwind this spring into a long chain, actually, it will also not be able to fit into this volume over here. So actually having a helical formation makes things a lot more compact. You can pack more into a single volume of space. Okay, so that's part C. And this also applies to glycogen, okay, because it's helical. It also applies to amylopectin. It also applies to amylose. Okay, so if you want to make mention of helical structure, you can mention that it aids in being a compact structure, so you can store more within a small volume of space. Okay, that's part C. Next question, question 3. They ask you to state the name of the monomer that makes up glycogen. Most of you got this correct, alpha glucose. Some students just mention glucose, but without mentioning what kind of glucose. You are expected to know what type of glucose is used to make glycogen, cellulose, amylopectin, amylose. So it asks you to explain the structure of glycogen and how it's related to its role in living organisms. First point, glycogen is a good energy storage molecule, as it is a large molecule that can be hydrolyzed into many glucose units for cellular respiration. So this one brings across the idea that you can store a lot of glucose units per glycogen molecule. And that's what makes it so large. Okay, and this is good. If I can store a lot of glucose, is good as a storage molecule. Points 2 and points 3 are very similar. It says that because glycogen is very large, it prevents it from diffusing out of the cell, allowing it to be a good storage molecule. Right, makes sense, right? Imagine if I store it as glucose, actually it can diffuse out of the cell very easily. And if it all diffuses out of the cell, actually I cannot really store it in the cell. But because glycogen is so large, it cannot really diffuse out of the cell. It's kind of stuck in the cell. Point 3, it said that large quantities of glycogen can be stored without affecting the water potential of the cell, as most hydroxyl groups of glycogen are involved in intramolecular hydrogen bonding. Okay, this is quite a mouthful. What this means is that the glycogen, okay, has hydroxyl groups. Okay, maybe I draw it a little bit bigger. Okay, the glycogen has hydroxyl groups, and these hydroxyl groups are pointing inwards, and they interact with each other, right, via hydrogen bonding. So let me use green to represent hydrogen bonding. So there's hydrogen bonding within the glycogen molecule. And these hydroxyl groups don't really interact with water that is surrounding it. Why? Because it's already involved in hydrogen bonding within the glycogen molecule. So these water molecules don't really interact with the glycogen molecule. And this is a good thing because a few chapters down the road, and in JH2 we talk about water potential. If it can interact with water, it can affect something called water potential and also can affect osmosis. Okay, so you can put a hold on this particular point. It will make more sense as we hit the later chapters. Okay, but the idea here is that it will not affect osmosis that much. Point number 4, glycogen is highly branched and it lacks hydrogen bonding that results in cross-linking. Okay, the multiple branching creates more terminal ends. Okay, what this means is this. Okay, as mentioned, the enzymes used to digest glycogen, amylose, amylopectin, they can only digest from the terminal ends. Terminal ends means this. So let's say I have an amylose over here. The enzymes can only kind of digest them from the ends. Okay, so here I have two ends that they can digest from. So they can snip over here and they can digest from over here. Alright. So here, amylose over here, I only have two terminal ends. Imagine now I have an amylopectin that has two branches. Now I have one end, two terminal end, three terminal end, and four terminal end that the enzymes can work on. And in glycogen, there's even more terminal ends. So imagine highly branched, right, that you see above. Lots of terminal ends. 1, 2, 3, 4, 5, 6, 7, 8. With all these ends, more enzymes can act on the terminal ends to hydrolyze and release glucose at a much faster rate. Okay, and this makes it really good because at the end of the day, living organisms like animals, they need these glucose they need to get back glucose much faster for cellular respirations as they're always on the move. Point number 5, again, it goes back to the helical shape of glycogen. Okay, helical shape means you can store more per unit volume, as we mentioned earlier. Okay, last part C. Question asks you to describe how the structure of cellulose is different from the structure of glycogen. Okay, this is a typical compare and contrast question. So other than comparing cellulose and glycogen, you may also want to do a comparison table to compare, and that you should also include a comparison with amylose and amylopectin. Okay, so that is something that you definitely want to prepare for. Okay, so let's look at the comparison points. In general, I do find that many of you are able to give the points of comparison. However, I want you to take note that you should compare point by point and not paragraph by paragraph. What do I mean by that? So let's take the first point as an example. Here, what we are comparing is the type of monomer. So it goes something like that. The type of monomer in cellulose is beta-glucose, while the type of monomer in glycogen is alpha-glucose. Here, I'm just comparing one thing. Okay, the next point. In cellulose, alternate beta-glucose units rotate 180 degrees with respect to each other, while in glycogen, all alpha-glucose subunits are in the same orientation. Okay, so this one has to do with whether the glucose flips 180 with every adjacent glucose. Third point, cellulose exists as a straight chain, while glycogen exists as helically coiled. Next point, cellulose is unbranched, whereas glycogen is highly branched. Last but not least, in cellulose, hydroxyl groups on the glucose subunits project outwards to allow interchain hydrogen bonding. So let's say this is one cellulose strand. All the hydroxyl groups project outwards, such that if I have adjacent cellulose fiber, they can interact with each other via hydrogen bonding. Okay, and this is between the chains, so that's why we say it's interchain hydrogen bonding. We can also refer to this as cross links because the links is across cellulose fibers. Whereas in glycogen, the hydroxyl groups on the glucose subunits project inwards. They result in formation of intramolecular hydrogen bonds. Intramolecular means that the bonds is within the molecule. So intra is within. So let's say this is the glycogen. You'll find that the hydroxyl groups are pointing inwards. So that means to say the interactions will take place within the glycogen molecule. It's intramolecular. We would say in the case of cellulose, this is intermolecular because it's between two separate molecules. Okay, the last one, part D, this is quite free for all. So most response I will have accepted. Okay, so we go back to part C. Part C, every time you do a compare and contrast, please compare point by point. What do I mean by that? Do not do this. So don't say, some students have a tendency of listing everything out about cellulose first, then they list out about glycogen. For example, they may say, okay, cellulose is made up of beta glucose, and every beta glucose unit alternate will rotate 180 degrees, and then they exist in a straight chain, and then it's unbranched. Then after that, in the next paragraph, then they describe that glycogen is made of alpha glucose, it doesn't rotate, it is helically coiled. So don't lump all the points of comparisons into two big paragraphs. Instead, compare point by point. Okay, it is easier for the marker to also find all your points when you compare point by point. One thing to take note of, actually, if you want to, you can actually give your answers in the form of a table. There's actually nothing wrong with that. Okay, but if you want to give your answers in a table, I need 3 columns from you. One of them is on the characteristics. Then the next one is on what you're comparing. So for example, cellulose, and then glycogen. Okay, you can actually do a table in your answers. Okay, so that's all for this particular video. Do go through your own self-evaluation to see where you stand. And if you need any support, please feel free to text me or to leave a private comment in Google Classroom. Thank you.